应该有个 view 吧？是在 view 里面 ？print 有没有个 present？ 没有。哎，对，应该可以。
好了，我就去加上我的 WP cover page。
好好，感谢感谢。So welcome to the machine learning seminar. Welcome to the machine learning seminar. Today I will discuss one paper, SeqGAN, sequence generative adversarial nets with policy gradient, and I'm Ray Lee, and supervised by Professor Wang. So the SeqGAN, sequence generative adversarial nets with policy gradient, is published in AAAI last year, and since the publication came out, it receives more than 100 citations, about 3 citations per day, about 2 or 3 citations per day. So this shows the GitHub information for this SeqGAN. It receives about 400 forks and started by more than 1,000 people. And the first author of this paper. 哦，就2点才开门吗？
开了，但是他要 work on 招生录取，我也不知道他们要干嘛。反正他们就今天2点之前不工作。
哦，好吧。
不接待我们。好。我先去下个卫生间，马上就。
哦，好。I will start presentation with online discussion between a researcher called William Wallace and a younger fellow. So 2 years ago, so a researcher William Wallace posed a question related to the generative adversarial networks for test. The question is, so what are some papers where generative adversarial networks have been applied to neutral language model? Hi. This is Wang 老师在这前面。 凑发邮件说凑回来，一周要照顾孩子，一周不回来。哦。你今天可以去吗？今天又不可以啊？那只能预。哎。你还要负责吗？该换人了吧？所以今天他负责吗？哦。
Sunday room. I'm using my computer laptop for the presentation, so unfortunately, and also Jinhong's iPad has low battery, so that's why we're using this computer.
You want me to bring my iPad?
That's okay. I think we're already set. So Jackie will handle the Skype.
Yeah.
She has the slides.
But she doesn't know which page we are on yet.
Okay.
Like
So
just facing
so the okay. So the
Okay, yeah, I can see the screen now. Thank you so much.
it's okay now.
Yes.
Okay.
So shall I start it? Yeah. Hello everybody, welcome to the machine learning seminar. So today we will talk about one paper, SeqGAN, Sequence Generative Adversarial Nets with Policy Gradient. And I'm Ray Lee, and my advisor is Professor Wei Wang. So this paper, SeqGAN, is published in AAAI last year. And since this paper comes out, it received more than 100 citations, about 2 or 3 citations per day. One citation every 2 or 3 days. And this gives the GitHub information. So currently, this piece of work, this product has been forked about 400 times and started by more than 1,000 people. And actually, the first author of this paper is an undergrad from the Shanghai Jiao Tong University. And he published many papers. This is one of it. And he got an offer from Stanford. Yeah, actually, he is applying PhD this year. So this is some background information. So before we talk about this paper, I will start the discussion from an online post. So 2 years ago, in 2016, a researcher, William Wallace, posted a question on Reddit related to the generative adversarial nets for test. The question is, what are some papers where generative adversarial nets have been applied to the natural language processing task? Because he saw plenty for images processing, but very few limited on the NLP task. And Ian Goodfellow, the inventor of the GAN, who is also the student of Banjo, so replied this question. And in the response, I highlight some key information. So Ian Goodfellow mentioned that the GAN has not been applied to the NLP task because GANs are originally defined on real value data. But for NLP task, we have each tokens, discrete tokens. For example, usually if we want to apply on the adversarial training, we have the generator and the discriminator. In the generator, usually there is a softmax layer. In the softmax layer, so whenever we want to generate token, we will choose the dominant token which has the largest likelihood. For example, now we output a word, a token, it's penguin. And somehow we pass this information to the discriminator. And the discriminator provide adjust a small number. Usually we call it a feedback or derivative. And in order to adjust the performance of the generator, we add the original thing plus this smaller value to adjust. But since the NLP task, each token is discrete, we don't have a word that responds to this penguin plus that smaller adjust value. Therefore, that's the reason why this GAN has not been applied to an NLP task for a long time. And also in this reply, the Ian Goodfellow encouraged people to use reinforcement learning algorithms to solve the NLP task. But he also mentioned that reinforcement learning doesn't work very well in his opinion. And he also mentioned that no one has made the effort to try it as far as he knows. So now, in today's presentation, we will talk about one paper, how he solved the sequence generation under the reinforcement learning and using the adversarial training idea. So before we dive into the details of the paper, I want to refresh our memory a little bit. So for example, in reinforcement learning, what are the key things we need to crystal clear? For example, I think the reinforcement learning regained his reputation or popularity from the AlphaGo project. So in the reinforcement learning, so we need to be clear about something. For example, what is the observation or what is the current state? For example, when we want to play this Go, the observation, the current state is given for example, 19 times 19 board. There are some piece, black piece and white piece on this board. And this is current state. This is our observation. And based on the current state, we need to take action. For example, now suppose it's the black turn. So our action is to put a black piece on the board. The action space is all the blank partitions in the current board. And after we take action, we need to define what is the reward for that action. For example, suppose now I put a black piece somewhere, and I can that action help us to win this game finally. Maybe we need to define a positive reward to encourage that action. So basically, next time we have the similar observation, similar state there, so we want to encourage that action. But if finally we lose by taking that action, no. Oh, sorry. What do you mean 2 types? This is a simple case. You can make it, yeah. You can make a larger reward, encourage more on that action, yeah. And also you can define a 0 reward because that may lead to both win and lose of the game. So basically, for reinforcement learning, we need to clear what is the state, and what is action, what is the action space, and what is the reward for that action. And here's something about generative adversarial training. So the basic idea of GAN is we need to generate something in high quality. For example, now we want to generate a special kind of butterfly which looks like a dead leaf. And also we have a discriminator functioning like a judge, telling us whether the things we generate is in good quality or not. Basically, it's real or fake. Initially, this generator is very weak. He can generate a butterfly, but the butterfly is not something we want. And this information is passed to the discriminator. The discriminator functioning like a judge, telling that, well, the butterfly you generate is not brown. This piece of information is passed back to the generator. Then the generator evolves next time. He generates a butterfly which is brown. At the same time, the discriminator also evolves. When this one is passed to the discriminator still can tell the difference. Well, the one you generate does not have wings. It's not something in good quality. And this feedback is also passed back to the generator until at the maybe third epoch or something like that. And when the generator generates something in even high quality, now this time the discriminator has difficulty in distinguishing between the fake and the real. And finally, at this point, so we conclude, well, now this time the generator generates some high quality things. This is the basic idea of GAN. So for sequence generation, there's one famous work proposed in 2014 in natural machine translation. And this framework is composed of one encoder and decoder, 2 networks. Each network is basically a recurrent neural network. The encoder encodes the sequential information, and at the when it encodes the last token, it has a last hidden state, a last hidden output. And the decoder uses that information to decode. For example, if we want to do the machine translation, it will generate token one by one based on the encoded information. So usually in the sequence generation, the object function, it usually is modeled by a maximum likelihood estimation scenario. We have a lot of input sentences, and we have a corresponding output sentences. For example, H here can be what's your name, and X here can be my name is Riri Li, my name is Professor John Cho, and maybe some other could be I'm happy, I'm Superman, something like that. And this X, both this H and X are sequence of tokens, and we use the XT to represent the Tth token in the output. The object function here is like this. So given a training pair, given the observation, input and output, we want to maximize this probability, right? How likely, given this H, the output is X? These are in the data. We want to maximize this probability, and this summation is over this H. And since we generate the token one by one, we can basically traverse the sentence through this partition, and we can use the chain rule to further expand this equation. This is the object function in the traditional sequence generation. So here, in this page, we show the framework of the sequence GAN. We mentioned that it's under a reinforcement learning framework. So originally, we have an input, a sentence H. For example, this H can be what's your name. And we have a model here. This model is defined by theta. The encoder here encodes information of this input, what's your name. And it further uses a generator to generate the corresponding output, X. X is also a sentence. For example, my name is Riri Li, could be this X. And this pair is passed to the, I call it a reward part. For example, I can use a human to annotate what's the reward and how likely this is a good response, good pair. Decoder we mentioned before. It functions like a decoder, yeah. Yeah. Yeah, it functions like the decoder, yeah. And therefore, we want to find a model. We want to find a theta that maximizes the average reward we receive. And how to get this average reward? We rewrite it in this way. For every input sentence, for example, how are you? What's your name? This is our H. And this pH gives how likely we observe this input in our data set. And for each input sentence, for example, H is what's your name? There could be multiple answers. For example, one answer is my name is Riri Li. The other answer is my name is Wei Wang. It's another X. And for every X, we know there's a conditional probability under this model. How likely when the input is H and the output is X. And we times the reward for this pair. So this gives the average reward for this system. Is that clear? Now we want to further derive what is this average reward. Now we are at this stage. So usually we have the summation and we have the probability here. Usually we will rewrite it in the expectation way, right? For example, given an input and how likely we will observe this input in our data set, we can rewrite it like the expectation of something, right? When the input, when this sentence follow the distribution in our data set. And in the inner summation, So similarly, we have a condition when we fix this h, actually h is fixed here. And when the output x, for example, really follows the distribution defined by the model theta. And the expectation, we want to get expected rewards for this one. And we combine these two, we move out this expectation outside. So we got this one. So given the input h, follow distribution embedded in the data, and when this input h is fixed, the output follow this conditional probability defined by the model theta.
Assuming we have a sentence H,
Yeah.
and you input it into the encoder and decoder,
Yes.
you get the final result X, and X might be several choices.
Yes.
And we can also assume that only one X is correct, and other are wrong predictions.
It's not a binary case, because we want to learn the sentence or the words dependency in the data. In the data, for example, if there's only one corresponding response, there's only one x there, then it's maybe this conditional probability will be high. But it's possible that there are multiple responses. For example, really appears 5 times, Joey appears 10 times. Then maybe Joey is a better answer. This conditional probability will be higher. Yeah. So usually, when we have an expectation, how do we get it? We do the large sampling, right? We sample a lot of input-output pair, and we calculate the average. That helps us to get this expectation through sampling.
This is all 2017, right?
Yes. Yeah. It's talk about how do we derive this reward. Up to this point, suppose we know how do we get this reward. What other issues do we have? We have the objective function we want to maximize. So usually, what is the next step? Usually. Yeah. Right. Yeah. Suppose we want to take the gradient ascent approach. We need to calculate the derivative, right? But actually, in this step, theta is our parameters. After the sampling, there's no theta. We can't calculate the derivative. Yeah. That's the first trick of this paper. Now here is the objective function. We want to calculate the derivative for this theta. Instead of doing the expectation, doing the sampling, we calculate derivative from the very beginning step. In the inner summation, the author times a conditional probability and divide the same one.
There is one thing that I want to mention. Can you go back one slide? Maybe one more. So this one, now maximizing no probability,
Yes.
maximum likelihood estimation.
Yes.
That is problematic in many cases. Why is it so? Because if you just try to maximize that probability, then what we can, just ignoring exactly what we use, like how we actually train it. If we just maximize that probability, then what we can do is that always we say we return one.
Sorry, what?
We return the probability one. All the time, we just return the probability one. Whatever pair you give, we just return the probability one. Then that maximizes things. So our model becomes whatever you input you give, whatever output you give, you always return the probability one.
The probability one.
Yeah.
Yes.
So that is the problem. And then I think that is reflected in the final derivation. Can you go 2 more slides? Here, right? So essentially, that is fixed, right? And then in some sense, that final result is implied by that maximum likelihood estimation.
Yes.
there seems to be, so the reason why we get this is in some sense because of the choice of the maximum likelihood estimation. So what I know for sure is that maximum likelihood estimation, unless we do some other trick, it is not a good optimization goal.
Yes.
I just wanted to mention.
Yeah. Yeah, I got your point. Yeah. We just output one, then that is maximized.
Right.
But the author in this paper, they mentioned that after, because the model theta, right, only stops at the sampling part. Therefore, we won't be able to, suppose we want to maximize this one using the gradient ascent approach. There's no theta in the object function. Then they play.
If we actually sum up with this value, right, whatever input output there, those are 1, right? Because those are correct answers. So the reward should be 1. Whatever input output,
just,
xi
yeah.
and hi values. So when you sum them up, it becomes 1.
It's fixed.
N,
Yeah.
right? N divided by N is 1.
Yes.
So here, that's an hour is 1. The reason why we get that formula is because of the choice of the maximum likelihood estimation. It just implies it.
Yeah. So in order to including the parameter theta in the object function in order to get a derivative, so the author put an extra entry in the inner summation. It times a conditional probability x given this h and divide the same one. And they play a trick here. The derivative of log of this fx function is equal to the 1 over this fx times the derivative of this fx function. And you can think this is our fx function, right? This is the right part. Then we replace this fraction by the derivative of this log fx function. And now this time, we still rewrite it in the expectation way. And we do the sampling. Now, in the derivative, we have something that is related to the theta. That is the first trick of this paper. Which means after the sampling, still we have something that is related to the theta. Then we can update this theta. Yeah, this is the trick. Is that clear? Which means really, after we do the sampling, maybe next time after we do the sampling, there's no parameter in the object function. We may want to explore. We may want to play this trick next time, if we have a chance. So when we do the gradient ascent, usually we have the theta defines the model, right? We have all the theta. This is the learning rate. Then we add up, we do the update by adding up the term here. And also we know how to calculate the derivative. And suppose we know currently how to give this reward. And we hope when this reward is positive, as we ask, it could be positive 10, positive 5, right? After we do the update, we want to encourage this kind of pair. Next time when we observe this hi, we want to increase this probability that given this h, we will observe this xi. And on the other hand, if the reward is negative, when we update this theta next time, we hope when we observe this hi, we will have less probability to observe this output, this xi. Now, let's compare. So before we talk about details of the paper, let's compare the object functions in the maximum likelihood estimation and the one under the reinforcement learning. So they are very similar to each other. The only difference is the reward here. Therefore, the author of this paper claimed that the one in the MLE is a special case of the one in the reinforcement learning. In this one, it treats every reward is equal to 1. So that's the difference they claimed between the object function in the MLE and the one in their paper. This one is a special case of this one. So this is the general training of the SeqGAN. So we have the encoder, generator, encoder, decoder here. And we have a lot of samples. Suppose we know how to calculate this reward. Then we know how to calculate the derivative. We do the update. And we repeat this process many, many times. And then finally, we can get a model, very good model. Now let's talk about how to get this reward. So before we talk about how to get this reward, let's assume, so what will happen if this reward is always positive? Now suppose we have a H here. H is, for example, what's your name? The ideal case is we know, or we can sample, we know all the corresponding output for this X. This X1 can be I'm Riri Li. The second one can be I'm Professor Wei Wang. The third one can be I'm Professor Jiang Chou, right? And for each one of, this is the original probability, conditional probability. And the green arrows indicates the reward. Suppose now the reward is always positive. And what will happen? Because we expect after when it receives a reward, we want to actually increase this conditional probability. But actually, its probability, the summation of these all the possibilities should be equal to 1. Therefore, what actually happens after the update, the one who receives a very large reward will increase. The one who receives a relatively small reward will actually decrease a little bit. This one also receives relatively large reward. After the update, it will increase a little bit. This is the ideal case. We know all the corresponding output for this input H. But usually, when we do the training, we do the sampling, very likely we won't be able to sample this one, for example, in one batch. Then what will happen after the update? This one receives a positive reward. This one receives a positive reward. And this one will be increased a little bit. This one will be increased larger than this one because of the larger reward. However, since we do not sample this one in the batch, after the update, the probability of observing this xi given this h will be decreased. But the ideal case is it should be increased or at least remain the same. But since we fail to sample it in that batch, actually after the update, this probability will be decreased. In order to solve this issue, the author of this paper simply just add a baseline, they call it, subtract a b from the reward to make it sometimes positive, sometimes negative. Suppose this RHIXI is always positive. So subtract a positive number here can make it sometimes positive, sometimes negative.
So P delta x HI, P delta x H, how do they constrain it?
This one?
Yeah.
What am I constraining?
So here is again is kind of along the same line that I have been mentioning.
Mm-hmm.
So if R is always positive,
Yeah.
then the P delta is always increasing.
Yes.
Right?
Yeah.
P delta is always increasing. So unless we actually add some more constraints, at the end of the day, what will happen is that every P delta of x over h is all 1.
No.
So we have to add some constraint.
All possible.
Right. So exactly how do you know how that is somehow expressed?
Expressed.
So do you renormalize after every batch?
renormalize.
Do you somehow add some additional structures inside whatever the network or function so that somehow that property is preserved? Or when you actually do the optimization, you add the Lagrange multiplier term so that it is actually summed up to one as an additional term. I'm just curious how it is done.
Yeah, thank you for pointing out, but to be honest, I don't know. The author didn't mention that. They only mentioned that the reason why they want to add a baseline here.
Because if you go back one slide, I don't know why this is a problem. It is not sampled, so I'm fine with decreasing it. It's not there. So why should I worry about this case? So to be honest, I think the reason why they're adding that minus b term is to make sure that it is not always positive. If it is always positive, then it will all go to 1, unless we do something special about it. So by actually subtracting some terms, we make sure that for some entries, it is negative. So somehow we kind of put the push as a downward force in training. In some sense, so unless you do something else, adding minus b that is essential. Unless you do it, it all blows up to 1. So I'm curious about whether they actually added, or they were doing already something to somehow add that constraint, or they are just using the minus b term as the constraint to actually make sure that it is not blowing up to 1.
I think in the paper they want to explain why they want to add a baseline and using this because of its probability. I don't think they put actual constraint in the network. Yeah, but another explanation as provided by Professor Zhang Chou is like if we do not add that baseline, and everything will go to 1 finally.
So I have a comment here. Actually, adding a baseline is not just for this particular paper. It's kind of a standard procedure in reinforcement learning. So probably there's a very nice lecture given by Berkeley some professor. Okay, so if you go through that lecture, you will see that the baseline approach is very standard. Because essentially the idea like a reward function, the relative value shouldn't be that important. Sometimes it could be positive, sometimes it could be negative. Of course, in this particular case, everything is positive. But somehow, if you shift it a little bit, the whole object function, the optimization point shouldn't change. Okay, so that's why in order to overcome this issue, they kind of introduce a baseline approach. And for baseline approach, the substruct B is kind of the simplest one. There are like more advanced ones to like treat as baseline. So just a comment here. Okay?
Yeah, thanks for the comments, Professor. So now, in the previous slides, we assume we know how to get this reward. We talk about, but we haven't talked about anything about adversarial training. We only talk about the generator part. We generate the X, and we assume we got this reward. And how to actually get this reward is to use the adversarial training. For example, in the adversarial training, we have the one generator that generates based on the input H, we generate the X. And for the discriminator, it's basically a binary classifier telling us whether the generated one is real or fake. Real means it's from the real data set. Fake means it's a generated one. And in the last layer is a sigmoid function. It will generate how likely this is real and how likely it's fake. And it's two-dimensional distribution. And we can compare that two-dimensional distribution with the 0, 1 because we either true or false. We can calculate the cross entropy. That cross entropy is actually used as the reward here. Why in the previous slides we assume this reward is always positive? Because the cross entropy here is always positive. That's why in the previous slides we assume this one is a positive number. That's where in this paper they use the adversarial training part. Is that clear? And still, we want to talk about this reward. When we can generate this reward, for example, the input sentence is "What is your name?" and suppose the xi is generated by the encoder, the generator part is "I don't know," and suppose we assume this is very bad answer, which means we observe very few such answers in the data set. And after we do the update, actually we are decrease these three probabilities, right? Given this input, I don't know. Right? This is the token at the first position. Given this input and the first token, the second token is don't, and the third one is no. After we do the update, actually we are decrease these three probabilities. But actually what we want is actually the first token actually is a good one. When I ask, what is your name? I'm something seems to be a very good answer. But actually, if we do the rewarding after the entire sentence, actually we are doing something wrong. Sometimes we are doing something wrong.
First of all, I don't understand why that is a bad answer. Why is it a bad answer?
Bad answer means this answer does not appear very frequently in the data set, even though it appears.
It doesn't appear very often in the data. What does it doesn't appear? So here, what is the overall? Is it a conversation?
No, it could be applied to conversation. It could be applied just the text. We want to learn the conditional dependency of the words of the sentence.
No. So what is the conditional dependency? So here, the input is somehow what is your name, and output is I don't know. This is not a translation, is it? It's not a translation.
No, it's not translation.
So here, in order to decide whether this is a good or good output from that input or not, we have to define what
is good.
Predict, right? So what are we trying? Are we trying to come up with a reasonable answer to that question? Or when you say something is bad, what does it mean?
Because, for example, in the data set, we have some sequence of words. Right. For example, that sequence could be "What is your name?"
Right.
And after that, the following words could be "I am somebody." We observe this sequence maybe a lot of times as a proper answer.
So here, the definition of good or bad answer or bad output is whether that particular sequence of words appeared in our data set as the immediate next sentence.
Frequently or not, yeah.
So that is our definition. And
yeah.
You claim that this is a bad answer because I don't know didn't appear very many times right after what is your name.
Yes, correct.
So that is that. And then you say that, here you do want to consider I as a good answer. Or
yes.
Because?
Because in the data we may observe a lot of following this xi, this hi may appear a lot of times in the data corpus.
I see.
This is only one instance for this xi, and followed by this xi. We may have another xg, and I am somebody, and another xk, I am somebody. So which implies I as the starting token should be a good one, even though in this case it's a bad answer. Yes. Yeah.
Why don't you
include x, h? We can. The answer is we can. The application, when we apply this on the dialog system, we want to include this h.
Also for translation, if you don't have an h,
yes.
could you determine if the x is equal or not?
We can evaluate that x whether it's meaningful sometimes. Meaningful means follow some.
Grammar is right.
Yeah, grammar is right.
But
The
E is not right.
yes.
You definitely should include the h inside the
Not definitely.
Where combine it as a pair. You have
I think the question to this answer is, can we come up with some application without considering the previous sequence? The X also makes some sense.
Before the discriminator is manual charge, right? In your previous slide.
Yes.
Can be replaced by a man. And when a man charge, if the translation is good or not.
It depends on the application, as you mentioned, right?
Yeah, right. You definitely need to look into the original case and also the translation after the decoder.
Yes. As I mentioned, it depends on the application. I don't know. In this paper, they also try to generate a speech. But for that speech, it also. But I think it's a minor issue. We can put a H here. But I think in this paper, I need to double check whether they put this H into the discriminator to generate a reward. The problem here is after we provide the input and after we generate the output, and after we generate this output, sometimes it's too late to give the reward. For example, I'm making this presentation, for example, and to the end of this presentation, Professor John Cho comment, "You made a very bad presentation." Right? That's the comment I received. Then I will start wondering. I'm making every slide is a bad one. Or starting from somewhere, I'm making a bad presentation, right? Which means we do not receive the reward instantly. Actually, whenever we generate token, actually we can generate some reward for it, telling us whether the partial sentence is good one or bad one. How do you do it in this paper, right? This is how do we calculate the derivative. And when we generate this response, actually we generate token by token from the very beginning, first token and the second token. So basically we add an inner summation here. So which means whenever we generate a token, we can do some update for this theta. How do you do it? For example, now the input is what is your name. I generate a token which is I. Then they go to the data side. They sample a certain number of sentences where the very beginning token is I. And for each of the sampled sentence, they can pass it to the discriminator to generate a reward. For example, in this case, we sampled 4 full sentences. I'm John, I'm happy, I don't know, and I'm Superman. For each of them, we can calculate a reward. Then it used the average of this reward as the reward of generating the very beginning token I. Because when in their training of their discriminator, the input is sentences. But if you pass in a partial sentence, for example, this I, the generator, maybe it will be able to generate some score, but because the training data is not look like this. Therefore, it tries to first auto-complete a sentence by sampling and use the average to derive the reward score for part of the sentence. Yeah, that's another trick in this paper.
Why Superman has a higher reward than?
Superman is a person.
It's not a name.
You ask, yeah, just an example.
And happy could be a name.
Yes, everything could be a name. Yeah, but just an example. Yeah. I think this trick is also popular in reinforcement learning. For example, when we play the Go, right? We have the current state, and we take action. We don't actually. After we take action, there's another state. That state could lead to the final win or lose. There are a lot of following actions, and they do some sampling. If that sampling, if a lot of samples lead to the wins, then that may generate a positive reward for the partial state of the, yeah. So actually, there's another approach to solve this problem. As we mentioned, when they're training their discriminator, there's an inconsistency here. They include this age. I need to double check whether they have this age or not. X is an entire sentence. Another way to train the discriminator is we generate more training instance. For example, for every sentence, in addition to put this I am John into the discriminator, we also put the prefix I am and I into the discriminator. Here, the positive and the negative means the positive directly comes from the data corpus, and the negative is generated by the generator. This is the real one. This is the fake one. This becomes the training data. Now, since we incorporate more training instance, that is the prefix of the sentences. Now, when we generate a token, for example, like I, after I pass this token into the discriminator, it will generate a reward that is more suitable, reasonable for to represent this data.
Policy gradient. I think, for example, like the maze. In the maze, you have 4 different choices of actions: up, down, left, right, and this is discrete actions, and we cannot use the policy gradient on them. This is discrete actions, and I guess for this case, we're sampling different choices of words for the next action.
The sample space is also fixed. Usually,
The sample space is still discrete.
yes.
Continuous. And how could you apply the policy gradient on it?
This is how they do it, by sampling.
Sampling means the next step might be A, might be don't, right? There are some choices, and the action space is also discrete, right?
The action space is always all the possible tokens. For example, they remain the most popular 20,000 words as the possible tokens.
Right. There's another example. If you are in the maze, but you can rotate, it means any angle you can, any direction you can go, and it's a continuous space.
First, it's not a maze. It's a chessboard. Even though you do the rotate, I think.
I just want to tell you that the difference is continuous space and discrete space. And in the continuous space, you can get policy. You can calculate the gradient. But in the discrete space, it's hard to calculate the gradient. And I guess this is still a discrete space for actions.
Yes, it is.
So I don't know how to calculate the gradient.
I think they use the equivalent default framework as previously to they update the theta in that framework. I think this is just how they get reward. This is my understanding.
Yes. Get a partial for a partial sentence, how to get reward.
So why what is the gradient?
I think the paper, when they talk about this part, it used a policy gradient as the subsection of that one. But maybe that confused Joey a little bit. But actually, this part tells us how to get a reward for a partial sentence.
Maybe this is the technique used in policy gradient?
Yes.
I know there are two different kinds of rewards. The first one is value-based, another one is policy gradient-based. Value-based is on discrete actual space, and the policy gradient is for the continuous space. So this is why I'm confused about this part. We can discuss it later.
Yes, right. Thanks for pointing it out. Yeah. And also, in this paper, it mentioned usually for adversarial training, it is hard to train this kind of network because we have two networks. In the generator, we want to solve some very difficult task. And the example could be we want to teach a kindergarten children to do the calculus. The kindergarten child is the generator. We want to teach this child to do the calculus, to do the task. So in the very beginning, it's very weak. The child is very weak. No matter what he tried, he just gets the wrong answer. That wrong answer is further go to the discriminator. And the discriminator will always generate a very negative negative value for that answer. So no matter what he tried, he always gets something negative. He don't know how to. Sometimes he don't know how to get the positive things. That's why they claim it's hard to train this kind of network. In order to address this issue, one possible way they mentioned that is like they use like a teacher forcing algorithm. They directly pass in the first phase of the training. They use real samples that are in the data and set the rewards for this pair to 1 to get the feedback for the generator, which means they provide some real examples instead of a response generated by the generator to update the generator. It's like when you try to teach a kindergarten child to do the calculus. First, at the jars, we provide something correct to the kindergarten child to guide him on the right track. Yes. Yes. Alternative way to train this work, they also mentioned is we can directly train the MLE model because the mathematical estimation is also in that model also has a generator defined by the theta. They can use that theta trained by the MLE model as the beginning states for this theta. That's an alternative.
You don't have much ground truth vectors. So, but afterwards you want to apply it to a large data set.
Large data set? No, that's. I don't think it's about large or small. The issue here is in the beginning, the generator is very weak. It always generates something wrong, something fake. In order to quickly improve this generator, we need to do something. Yeah. One thing is to using some parameter that can be well trained by some other method, for example, using the MLE model. Or, as they mentioned, directly using the real example, pass them to the discriminator, and using these correct examples to adjust the parameters theta.
How do you use the real data to update parameters? Because the fake data depends on the parameters theta.
Yes.
Here the real data is not. How does that background work? Just replace this.
I guess it's just for updating the discriminator.
Oh, okay, I see. Okay,
Yeah. So here's the evaluation of this this work. So the first experiment they conduct is on the synthetic data side. They just use LSTM. The parameters in the LSTM are just random. They didn't train it. But based on this LSTM, it can generate a lot of sentences and treat it as the real data. And they use their model to learn the real data. And also they run some other different process competitors. Now given some input, given the age, the generator, the model they trained can generate some corresponding output. And then they compute the log likelihood between the one they generated and the real one, the real output in the data set to quantify, to evaluate the performance. And for this negative log likelihood, the smaller the better. And here is the result. There is a random algorithm. There is one trained under the maximum likelihood model. There is a scheduled sampling algorithm. There is a positive gradient Bloom method. And the last one is their SeqGAN method. And they conclude their method achieves the best performance because the negative log likelihood is smallest in this comparison. And this figure shows the performance of different algorithms as they increase the number of epochs. So actually, some people actually attack. Most people, they like the citing because the LSTM is just generate some random things. It's not a superphysical novel. But most people put comments here. It seems like for these competitors, after the 150 epochs, they stay on a local minimum. But for the SeqGAN, it further dive into either the global minimum or another better local minimum. And they challenge that maybe when they increase the number of epochs, this algorithm may also be able to find that local minimum, that global minimum. Clear? In this paper, they also conduct some experiments on real data. For example, they try to generate Chinese points. They want to generate speech, Barack Obama speech, and also music generation, and conduct some user study to demonstrate how good the algorithm is. But in the slides, in the presentation, we didn't show it. So instead, we show something from other researchers. So in the paper of adversarial evaluation of dialogue models in NIPS 2017, last year, and two people one from Google, and the second author is Aurel Vinyals. Actually, he's the one who proposed the sequence-to-sequence model in natural machine translation in 2014. So in their paper, they have one sentence to comment this work. In this paper, they try to use the adversarial training, use the discriminator to automatically evaluate the performance of the generated response. In their paper, they mentioned for this kind, still more needs to be understood. And using the discriminators alone won't solve the evaluation challenges of the dialogue system. This is about their paper, right? The next sentence, despite the fact that GANs do not use extra information than was already present in the training set. So even though some work argue that it's a better loss than the likelihood. So this work is actually refers to the SeqGAN. So remember that the difference between this reinforcement learning work and the one in the maximum likelihood, they used both. They didn't. The reinforcement learning one didn't use any other information that is not in the training set. They used the same information. That is the comments from some other researchers for this paper. So even though they receive a lot of citations, but still some people still do not believe this is a great work. But at least it opened a new direction how to apply adversarial training on the NLP task. That paper? Yeah, maybe next time we can talk more about that paper. Yeah. Yeah, actually that's all I want to present about this paper. So let's recap a little bit. So first, we try to derive the rewards function we want to maximize. And we found that in that object function, we don't have the theta. Therefore, they play a trick to, in the inner summation of the conditional probability, that part, we times entry and divide by the same value. And we can use the derivative log something. And in that allows us to include that theta in the object function. Then we can take the derivative. Then we can apply the gradient ascent to solve this problem. And the model used the generator to generate the, given an input h, given a sentence, generate corresponding output x. And given that x, maybe together with that h, we can calculate the rewards using the discriminator. In the last part of discriminator is a binary, two-dimensional distribution. We can calculate, compare with the real 0-1 distribution to calculate the cross entropy. That cross entropy is always positive. And that positive value is used as the reward. And after that, they try to subtract the baseline to make it sometimes positive, sometimes negative. And what others? And in the evaluation, they try to generate a random stuff as the real data, and try to learn, try to train, try to fit their model on this real data, and use the negative likelihood as the evaluate function. The smaller the better, and compare with different methods. Yeah, that's basically about this work. Any questions?
I think I have a very high level idea, but somehow the details are somehow eluding me. What is the core challenge? The core challenge, so GAN, we have the generator, we have discriminator, right?
Yes.
And the way that we train it is that first train the discriminator by taking half of the data from real data set, half of the data from the generated data set.
Yes.
Somehow we want to train it so that discriminate as much as possible.
Yes.
So we train the discriminator. And once you do that, then we train the generator so that the difference is as small as possible. So it somehow rank the generated data as close as possible to the true data. That's how we train the
Yes.
generator.
Yes.
And then repeat this process and eventually somehow we get a good generator. That's
Yes.
the high level idea.
Yes.
Now, here I think the main challenge of applying that to any sequence data or language data is that when we generate image data, for example, the output from the generator has a continuous value.
Yes. Pixel.
So
Yeah.
when we backpropagate the difference through that data set that is generated, there is that difference, so we can actually backpropagate the generator.
Yes.
So that is why there is no problem. But once you have discrete data, like the sequence data, language data, then there the difference, how that output, right, all these discrete values. And then when you have to try to backpropagate the difference through that generated data, it is not clear how to subtract that small value, right? And how, it's not clear how to backpropagate it.
Yeah, because we have softmax layer in the middle, right?
Right. Well, it's not really the softmax layer. It's really about what's the difference there, right?
What's the difference? The difference is the input for the discriminator for the NLP task is discrete tokens.
Right.
Yeah.
So here, are we still able to compute the difference and backpropagate, or that's not an issue? I think that is the core issue, and that they try to get around, no?
Sorry, what? Could you
So
please?
here, I think that I'm just trying to understand it better. So here, we have the generate data,
Yes.
which is discrete values, right? 1 or 0.
For NLP task.
For NLP task,
Yes.
right? For every word location, we have one discrete item.
Yes.
Now what do? So we backpropagate, right? From the discriminator. And now, what do we have? For every word location, we have some errors accumulated, right? We have some error accumulated, and then we want to backpropagate it through that data.
Uh-huh.
But how do we do it? Is it possible to backpropagate through that layer?
I think from the at least from the conclusion from the inventor of this gun, he mentioned that from this part, there's no way to.
What is the error? The error is we have some values, and then for every output there is input, there is output, and then subtract it.
I think what it means that you can still do some, you can still get some small change, like penguin plus 0.0.
But that may lead to the same output again.
Right.
Yeah.
It's always slight change around the word.
Right.
I think that's the core issue.
Why is it core? Why is the so here as long as we can train, we don't have any problem, right? The question is, are we able to train? That's the no, or is that a problem?
I think he says.
I think the
suggests yes. You can make slight changes. Only
we can make slight changes. For example, we add a very smaller value,
Right.
but that smaller value in the next iteration will output the same token again. As you mentioned, it's if it's at a 0, 1, that partition is still 1.
So training is not an issue. Output is an issue. Maybe I need to.
I think training is related. So I think training is also an issue because of this. Because as you said, the second iteration, you will still output the same word penguin. So you will get the same penguin.
So when I listen to what you present, I see a lot of cute ideas about, I think, this derivative gradient and somehow being able to keep it. Those are actually beautiful ideas. I
Yeah.
love them. But I still kind of have a difficult time of exactly what is the core issue And then how these
overcome that
or
issue.
how these tricks are able to overcome those issues. That question is not very intuitively clear to me.
Sorry for that, because when I read this paper, I also have this problem, right? And how they overcome this issue. It's still, for me, it's like it's not very clear even to me. Yeah.
Did you ask it?
Sorry, I haven't.
So basically, do they solve this problem? Like plus 0.001, you get the same. Do they solve this problem?
No, I don't think they directly solve it. At least, for example, from their objective function. What are important just the derivative.
Right, so maybe still a slight change. So maybe still output the same one. Like here, you update the parameters data.
Yeah.
And so the next iteration, you will get a slightly different word.
But
But there's no guarantee.
Right, that's the question.
Yeah.
They can run again,
So
right?
maybe still come. That's my question. Is that possible?
the problem, I think, the question is whether that smaller update will accumulate or not.
Right.
Yes.
Maybe it will, by many iterations later, it will gradually be pulled towards the next word.
I don't know if we can probably not.
Yeah, I will double check that with their code. From the paper, I cannot tell. Yeah.
I mean, the
At least that is the
traditional
whole.
one doesn't. I mean, the traditional model doesn't.
They claim.
I think that is the power of the reward signal somehow, because the reward signal will pull it, and instead the distribution will be pulled upwards and downwards. Right? So can you go to the distribution with the three blue bars, this one? I think do they basically, at each iteration, do they just take the max, the word with the max normalized probability to output?
They don't mention in the paper. The paper is very short. Yeah, we need to double check the code. Yeah.
I think that's maybe where it becomes better.
If it don't use the softmax, that skip that part maybe. Yeah. Yeah, I will check the code. Yeah. Any more questions? I will check the code and get back to Professor later. Yeah.
I'm just very curious. This is very interesting.
Yeah, because when they explain, when the author of GAN, when I read this response, it still looks a little confusing to me. I know it's the token is discrete, and he explained this discrete something plus a very little update. Next time, there's no such word correspond to this little update. I think the question is whether this little update will accumulate or not. It will accumulate during the training process. It may lead to a different token.
I think
Yeah.
there's another problem in NLP is that there is a grammatical constraint to the words. In the images, you don't have this constraint. But I think the way they solve it is to use RSGN. Hopefully that will better capture the semantic relation. That is one reason. Although
Yeah.
you didn't mention here, but I think
Yeah, that part can be captured by the LCM, by the RNN part. Yeah.
partially is.
But then I read when you didn't copy the full paragraph after very last regarding the comments on RNN.
Because it's too long, I only, yeah.
But he believes say that RNN should work, right? That's just
RNN, yeah. For this part, some people said that GAN does not work on the RNN.
Yeah, but then what the last sentence? But no one with serious neural network what?
Yeah, I will check the full response. Yeah. Yeah.
Do you have some time after 10 minutes?
Yeah, sure. I have.
You can come to my office and then try to explain the paper.
Okay,
We
sure.
can go over the paper
Yeah.
together.
Yeah, sure, sure.
So that you can make a meaning of individual formula.
Yeah, sure, sure.
You can figure it out more quickly together.
Yeah.
That's good for today.
Yeah, that's
Next
it.
week we'll invite Jiaqi to here to talk about mining.
Unsupervised rare pattern mining.
Unsupervised
Rare pattern mining.
writer pattern
Mining.
mining or writer pattern mining. Oh.
And there is a simple survey first, and then my own work.
I see. Okay, good.
That's it for today.
Okay,
Thank
thank
you.
you.
Thank you.
So come to my office maybe 10 minutes later so that I can quickly scan through the paper.
Sure. Yes, thank you.
Thank you.